All right. Hello, everyone. This is Dr. Daniel Jude. I am re-recording this lecture so that there's sound associated with it. Um, so, a few things about me, right? I need to update one of these slides in here, but it's fine. So, I am Dr. Daniel Jude. I hold a PhD in criminal justice. And I have a background in criminal justice, law, sociology, marketing, statistics. I'm currently adjunct professor for the Kent School and a data scientist for Brown Forman, which is Jack Daniel's family brand, essentially. You can contact me using several methods: cell, email, Facebook, or through Blackboard. Although I really prefer you not message me on Blackboard. And I'll go ahead and update that. So you can check the syllabus out, and when you just take a look. I'm not going to go over it in the video, so just have a read. If you have any questions, feel free to send me. Now here is where I kind of go on to the reindeer lecture, and what this is about is that you cannot prove a negative. Okay, so what do I mean by you cannot prove a negative? Well, to say that you can't prove a negative essentially kind of boils down to when someone says, "Oh, hey, there's no fish in that pond," right? Well, can you actually prove there's fish in a pond? Well, you can look, but you can see there's no fish. You can dive down in there and you can look and hide and look around for more fish. You could do a whole bunch of tests and still find no fish, but you still can't conclude that there's no fish in a pond because, well, there still could be. You didn't overturn every rock. It is very easy to miss things. Therefore, you can't really prove the non-existence of something. Okay? You can provide evidence that something doesn't exist, or you can provide evidence that there is a lack of something, whatever you're talking about. But you can't fully 100% say, "Oh, hey, there's absolutely zero fish in that pond," and then because that's going to you can't make a factual argument about it. So we can even take this to the point of Santa Claus and reindeer. Well, in order to scientifically try to prove something wrong, which we can't, we can try to provide evidence of something. Okay, so let's try to test is the correct word here. Test if reindeer can fly, which is part of the Santa Claus myth. And the Santa Claus myth, as most people may know, states that every night on Christmas Eve, every year on Christmas Eve, Santa Claus hooks up a bunch of reindeer to his sled and he takes off and flies through the night sky, delivering gifts to all the children of the world. Well, we can test the fact of flying reindeer or the lack of fact of flying reindeer. So what we're going to do is we're going to capture 1,000 reindeer in the northern parts of Canada, and then we're going to load them up on a truck, and then we're going to take them to New York City. So what we're going to do is we're going to look for the tallest building we can find in New York City, and we're going to haul these reindeer all up to the top of this skyscraper. Let's say the Empire State Building. It's not the tallest, but it's a good one. Okay. So we're going to make numbers, and we're going to put reindeer 1 on reindeer 1's side, reindeer 2 on reindeer 2's side. And what we're doing is we're making data points. Okay, each data point of data is a reindeer. So again, reindeer 1, we record reindeer 1's weight, height, if it's male or female, and the last box says flies, yes or no. So what we're going to do is we're going to take all 1,000 of these reindeer and we're going to number them 1 through 1,000, and then we're going to take them to the edge and we're going to shove them off. Well, that reindeer didn't fly; it just went splat. So we're going to continue. We're going to continue pushing these reindeer off until we're finished. All 1,000 must be pushed off this skyscraper in order to conclude this test. odds are that 0 out of 1,000 float. Now, what this means is, and I'm using this very exaggerated answer to really drive the point home, is that the 1,000 reindeer we had just didn't fly, or they chose not to fly. They didn't fly, they could not fly, they chose not to fly. There might be some reason they didn't fly. Okay, but all we can say is the 1,000 reindeer that we decided to test chose not to fly. But we can't prove that reindeer can't fly with just that test. Now, that provides evidence on the table that reindeer can't fly. But there's other factors to keep in mind, okay? So the North Pole is a special place, where Santa Claus is at. So there could be a specific barometric pressure that make reindeer fly that is only exclusive to the North Pole, that they can only take off in the North Pole, okay? And it's not to say they can't fly around the rest of the world, but they can only take off in the North Pole. Or it has to be a certain temperature. Maybe the temperature was off and they did that. Or maybe it requires the presence of Santa Claus. Maybe the whole thing is Santa Claus weaves his magic on these reindeer and they fly as a result. Maybe they need a particular red-nosed reindeer guiding them. Maybe the reindeer just weren't in the mood to fly and they chose not to. They can always decline to fly and just tumble to their death. Regardless, the 1,000 reindeer we tested did not fly, so we can file this as evidence as reindeer cannot fly. Now, what we can further test this by picking different cities at different latitudes and longitudes at different temperatures. We can mix and match this 1,000 reindeer sample in different parts of the world, at different latitudes, at different temperatures, at different times of day. All the factors that you can think of that you can be changed and worked around, and we can test all these things with 1,000 different reindeer. So we can do that, and odds are every time you shove a reindeer off the top of a skyscraper, it's going to tumble to its death. So we can pretty conclusively say that reindeer can't fly, but we can't say we can't say 100%. And as we take this class and as we go through this course, you'll find that we will start measuring things by percent accuracy. 95% is the gold standard, although 99.9% is what you're looking for. We'll get into that when we get into that. But that's what this is about. So how do you use this? Okay, well we use this with saying, okay, so let's say you're a social worker and you're trying to figure out a program that benefits recovering drug addicts, right? So, what intervention works? Does cognitive behavioral therapy work? Well, let's say rehabilitation. We'll say that rehabilitation works in 1,000 of 500 in the urban areas, and we can conclude, it's 97% accurate, so let's go and test it in Cincinnati versus test it in Louisville. And we'll see if testing these, the intervention, in this case rehabilitation, results in, someone becoming sober. And that's kind of how we test the efficacy or the effectiveness of programs. And it's one of the ways that as social workers, as nursing students, we can find reliable methods to treat people. So that's what this is about, and I'm going to move forward. This is the wheel of science. It works in theory, hypothesis, observations, and empirical generalizations, or it goes either way from induction or deduction. With deduction, we start with a hypothesis, and we move on to observations, and then move to empirical generalizations, and then finally we arrive at theories, okay? With empirical in which we form hypotheses with. There is a difference between theories and hypothesis, okay? A hypothesis is a stated relationship between two variables or more. Okay? Not a theory. For example, a hypothesis would be, as the temperature outside increases, ice cream sales will also increase. That is a hypothesis. It's saying that if the temperature goes up, ice cream sales will also increase as a result of the temperature going up. Now, a theory is a more systematic thing. It's saying, okay, it's kind of like baking a cake, a theory is, okay? What a theory states, and I'll go to social disorganization theory in crime, is basically saying that, hey, if everything is present in this mix, a crime will occur. We'll use a simpler one. We'll use routine activities theory. So that's a very simple theory, routine activities theory. It states that if three things are present, a crime will occur. 100% of the time, a crime will occur. So these three things are a motivated offender, Someone that wants to steal something, we'll use theft. Someone that wants to steal something is looking for something to steal. So there's our motivated offender. Number two, a lack of a capable guardian. So what is a lack of a capable guardian? It's something that's not monitoring what the thief is after. It could be cameras, for example. It could be someone just standing guard. It could be even a child there that's able to witness what's going on, so they'll be able to run and tell on someone. It could be a well-lit room. There's a lot of capable guardians. You know, the ATT sign up outside of some of y'all's lawns is a capable guardian because it deters people from wanting to break and entering because they know that you have a armed system, for example. And the third and finally is a suitable target. So a suitable target is anything that the thief wants. Okay. So what's a suitable target? Let's say I'll give an example. If anyone is knowledgeable of the 1980s floor model TVs, those things never got stolen. Not compared to the TVs of the day. Why did they not get stolen? Well, the reason why they didn't get stolen is because they weigh a metric ton. Okay? So no thief's going to run into a house and try to pick up one of those TVs and haul it on his back to get back to his truck. It's just not going to happen. Whereas, you know, you get these flat screen TVs today, you can grab one by yourself, 50-inch one, right? It's not very hard. You just, it's a bit awkward to do it by yourself, but you can. You can grab it and run out the run out the door. So those three things have to be present. The suitable object, in this case, we'll say a ring left laying on a table. Okay. A motivated offender, which is a thief who's just looking for anything valuable that he can pawn off. And then finally, he stumbles upon the room. He sees the table. He sees the ring on the table. Looks around. There's no cameras. Looks around. There's no one inside. He's going to run in there, grab the ring, pocket it, and then walk out like nothing happened because it's now a ring in his pocket. Who's going to look in his pocket? And it's so little that it's very easy to steal, making it a suitable object. So those three things. That's a theory of routine activities theory. It's how and it's good to explain victimization. So that is a theory. That is not a hypothesis. Remember, a hypothesis is a stated relationship between multiple variables. So anyway, if you inductive thinking, you start with empirical generalizations, and then you move on to observations. Okay. With induction, you start with the hypothesis and you finish at theories. So this is where I talk to people in person. Since this is not an in-person class, I can skip this. So the reason why we use stats is scientists need to know what works and what does not work, as I was talking about with the reindeer slides. So statistics are used to identify evidence-based practices. And then for this class, we'll emphasize interpretation over calculation. So we're not going to worry too much about the mathy bits in between. What we're going to worry about is like what's actually going on with the conclusion after we finish the project. We can go ahead. This is something just for your own personal notes. Some definitions for you to look at. I kind of talked about these definitions already, so we'll skip through here. Qualitative versus quantitative and program eval. So what a quantitative study is, and what this course is about, is it's based on numbers and observations, when it tends to have a larger sample and broader pool. So what we're going to do here is we're going to do a lot of spreadsheeting. We're full quantitative here. We're full math. But again, we're not going to worry about the math, and I'll show you. We're going to be very working with Google Sheets and Excel. Program evaluations where social work tends to be at, and it's focused on our real-world solutions. We go in, and let's say the living room project or a homeless shelter. We go in and we take a look at what's going on in the homeless shelter, and one of the big questions we ask is this an effective program? Okay, does the program accomplish what it seeks to do? And if it does not accomplish what it seeks to do, what can be done about it? Does it need to be defunded? Does it need extra funded? If it's not working at all, it's best to take that money away from that program and put it into better use in trying to help someone else. Even though as heartbreaking as it is for someone's personal pet program to be defunded, the ideal here is to help people, not to help social workers succeed. It's more we're in it to help people out in general. So we got to make sure we're providing them with the best we can get to them, or at least providing them with something that actually works. So each unit, which measurements are a record. So let's start breaking down this course, okay? So there's a few terms in the course that you're going to need to know, okay? Unit which measurements are recorded is a case. In case, social work are typically individual people. Now let me read that again. Unit of measurement, okay? I'm not going to read it word for word here. I'm going to break it down. A unit of measurement, and this is your very first lesson. You're going to be asked this question quite a bit. A unit of measurement is, in our case, people, okay? Sometimes a unit of measurement, it can be cities, states, zip codes. It can be people. Uh, a unit of measurement is basically what your study is about. Is it about helping people? Well, your unit of measurement is now people. Is it about the crime rates in a particular geographic area like a state? Well, your unit of measure is a state because you're looking at Kentucky versus Ohio, okay? Unit of measurement is broadly termed the subject of your study. So what is a variable? Variables are everything in stats, okay? It's an ingredient in data that is something with more than one value. For one, left-handed or right-handed, and you would code this as left equals 0, right equal 1. But a variable is, in this case, what's your dominant hand? So the question would be, what's your dominant hand? And there's two variables here. I guess there's a third one, too, for ambidextrous. But they could enter left-handed, right-handed, or ambidextrous, and that would be how the dominant hand varies. So variable varies. How that question varies is the variable in that question. So the three variables in this case will be left-handed, right-handed, or ambidextrous. Age is also a variable. When you ask about age, you can be 1, 2, 3. All those are variables. So what particular age you are. Constants are the opposite of variables, and if constant remains the same, if all cases in the study are female, then female is the constant. So if everything's the same, it's a constant. If it changes around, it's a variable. Hopefully that helps with that discrimination. So we now move on to here, okay? So this is very important, and people ask me all the time in this course, where can I find this information? Because I can't find it anywhere in the slides, and the answer is it's in the beginner slide, okay? What types of variables we can look at, okay? So you have categorical variables, and they're often called nominal level variables. They have non-numeric values. An example in this case would be like eye color. You can't rank order eye color because brown versus blue versus green, they're just the existence of color in eyes. You can count them. Sometimes there are higher amounts of them, but the actual eye color itself has no inherent higher value than blue or brown, okay? Race is another one, okay? You cannot rank white over black or black over white or Asian. You can't rank order race, so therefore race is what you call a nominal or categorical variable, okay? We assign these numbers anyway as identifiers, but that's not a number ranking. So like when we assign the number 1 to white, and if we go race, what that means is it is ID number 1. And that ID number 1 is no more bigger or smaller than your own personal Social Security number. Again, your Social Security number is a categorical number. Now, it's a categorical piece of data because it is a serial number that does not rank or does not have a weight to it. In other words, if someone has a Social Security number of 4567237 whatever, okay, then the person with a Social Security number of 467 is not higher ranked than the person with the 457 Social Security number. They're just identifiers. So moving forward. So let's talk about categorical variables a little bit more. You can sex be a dichotomous with male 0, female 1. Gender is not a dichotomous variable. They're different. So we can talk about one or the two. There's other branches as well for those. Numeric variables have several numbers, and the numbers have values. So what's a numeric variable? Well, they're called interval ratio variables. And again, I'm going to underline, they're called interval ratio variables. Write this down. They're called interval ratio variables, numeric variables are, and we'll talk about them as we move forward in the class. And what a numeric variable is as you probably think, it is a number it is a variable that we can assign a weight to via number. So, for example, height. A larger number is assigned to height, then we know that that person is taller. And the same as the lower the number on the height, we know that person is shorter by just looking at the number. Therefore, those numbers have weight. So exam scores are numeric. As exam scores increase, exam scores increase, then we know that the score is better. Samples and populations. Okay, so there is a difference between the sample and the population. Just so you know, we'll use the University of Louisville as an example. And the population of the University of Louisville is the entire university. Every student that goes to school at the University of Louisville satisfies that requisite to be a part of their population. So what's a sample? Let's say that every student in this room is just a sample of the greater population of the University of Louisville. And so let's break this down into our class. So now let's move and shift so that we zoom in, and suddenly now the population, because it's the only kids we have in the study, the population is now the classroom. Okay, so let's talk about this in a smaller lens. So let's say the population is our classroom. I want to have a sample of students in this classroom, so I'm going to randomly pick 7 of you. Those 7 students are now the sample because I pulled them from the population. The greater number of population will say 22. We pulled 7 students we sampled 7 students from a population of 22. So, we'll say we do it randomly. Okay, and it'd be a random sample. So a population, as you can see in the side here, you can read that on your own, and I can talk about and try to give you more material via that, because me just reading your slides isn't very useful. So descriptive stats, their name as the name suggests, they describe the sample of the study. So when you're talking about descriptive stats, you're talking about what your unit of measurement is. You're describing your unit of measurement. So let's say we use people as our unit of measurement. So we have 50 people in our study, and we can say, for example, 72% of our study, the people in our study are white, 48% are female, and 32% have blue eyes. And that would be describing the overall unit of measurement in the study. And you're pulling your averages and the means and the medians and the modes, which is mean and average is the same thing, of all those things. And those are descriptive statistics, okay? Answers questions such as, is the sample mostly male or female? What is the average age? What is the common political affiliation? So on and so forth. Inferential stats are then used to draw conclusions. So you could say, back to the hypothesis thing, let's say that we made a hypothesis stating that the more you study, the better your grades are. Something very non-controversial. And we take a sample, we record the grades of all 20 of you all in the class, and we also have a thing where we tracked how long you were studying for. And we could see in this thing, the more time spent studying, the higher that person's grades were. And conversely, the lower time they spent studying, the lower their grades were. So the inferential statistic would be higher study times result in higher grades. Okay, even though it's a statement, that is an inferential stat. So the following 2 slides will provide an example of each. And you can see here, descriptive stats. I'm not going to go too much over it, but you can see, and I'll go over this when we get back to it, okay? So univariate statistics pertain to a single variable at a time, and univariate stats look at one variable and that's it, okay? So univariate uni equal 1. So political opinion on an even, for example, is univariate. On an event, for is univariate. Bivariate convey the relationship between 2 variables, age and shoe size, for example. Geez, I made a lot of typos in this. And multivariate statistics involve 3 or more variables at a time. It often concerns if one variable impacts another. And this is where confounding variables come into play. So bivariate, let's go over this again, okay? So univariate, you're just reporting one, let's say, eye color. And you can say, well, the mode eye color is brown. That would be a univariate statistic. Bivariate is the relationship between 2 variables. Again, as test scores, as study time increases, so do test scores. As a bivariate relationship is the relationship between 2 variables. Multivariate is multiple at the same time, and it's saying, so what multivariate handles is, let's say that we are now looking at, I don't know, grades and time spent studying. We'll branch this out into multiple variables, okay? So we can say grades and time, the more time you spend studying, the better your grades are. But what if we add into this a unstable home? Now we have a third variable floating around, and we can see that even though as more time spent studying results in higher grades, an unstable home will impact the scaling of that increase. And what I mean by the scaling of the increase, let's say that someone with a very stable home, they can see a result, a 2 times increase in their grade if they study the exact same time as someone who has an unstable home. The unstable home will still see positive returns, just not as much as the person in the stable home. And that multivariate statistics will allow us to examine that. So we learn multivariate statistics last, but it also is how you look at the whole picture. So multivariate statistics is about that whole picture, whereas bivariate is kind of like an isolated picture, and you use both in the same project, essentially. Percentages, averages, and the graphs can be used to describe univariate statistics. Summarizing the income and distribution of a community, you can do this with the graphs like a pie chart. You could say, okay, in St. Matthews, you could just grab the income of everybody in St. Matthews and then rank order it with working class, middle class, upper class income if you want, and just kind of graph it out in a pie chart. Or average income, which is one number. In this case, you could just take everyone's money that they earn in St. Matthews and average it into one final number, an average of I'll give a crazy example, $5, okay? So bivariate, we kind of looked over there. Now here, the time studying the grades. So here's a class question. Which is the independent variable and which is the dependent variable? So what's an independent variable? An independent variable is standalone, and the dependent variable depends on that standalone variable. Okay? So the dependent variable in this case would be grades. Why? Because we're saying that the person's grades depend on how long they studied. Okay? So time studied is the independent variable, and grades are the dependent variable. Get to know those two terminologies very personally because you're going to be using them a lot in this course. If you get that wrong, you probably won't be able to pass. So make sure you know the difference between a dependent variable and an independent variable. Again, it's in the keyword depends on, okay? So does time spent studying always impact grades in a positive manner? The answer to that question is no. Sometimes you can overstudy and burn out, and it might reduce returns, okay? Let's say you study for 9 hours, but after like the 4th hour mark, it's just not being effective anymore, and that matters. And that's when you're looking at multivariate stats. It's like, well, what's the actual duration here? Are the returns even? Random assignment is the process in which objects are assigned to groups. Intervention is the thing that is done to intervention group or experimental group. Behavior modification problems, marital therapy, so on. In other words, let's say that you have a married couple that can't get along. Well, in order to intervene and try to save that marriage, we put them in marital therapy. So marital therapy is the intervention. So, and then 2 interventions presented a computer tutorial program or TA. Once the students select, the professor will evaluate which option was more effective at the end of the semester. So what we're doing here with this 2 interventions schema is that we're comparing a computer tutorial program versus a in-person tutor. And we'll evaluate which students had which was more effective for the students. And that's 2 interventions. We're testing the difference between 2 interventions. 4 levels of measurement: nominal or categorical, ordinal, interval, and ratio. Let's go ahead and start breaking these down. We broke down nominal already with the eye color, the race, everything, all of that, okay? We don't have to worry about it. Ordinal, we haven't covered. So ordinal is a level measurement variable. Have rank ordering, but not necessarily numerical, but can be. An example includes social work, social class, working, middle or upper, and opinions on a survey. They agree or disagree or no opinion, and above or below the mean measures, 0 or 1. So these items are ordered in rank, but but the distance between the items cannot be discerned. So okay, let's talk about this. Okay, everyone is familiar, or at least I think most people are familiar with these kind of like scales where it says strongly disagree, disagree, neutral, agree, strongly agree. That is ordinal scaling. So why that's ordinal scaling is that strongly disagree we know is the most negative answer, and it's more negative than just disagree, okay? But we don't know how much more it is. I mean, anyone could have a different kind of floating number in their head, but we kind of understand that disagree and strongly disagree are just two different things. One being more negative than the other. It's in the same way on this agree versus strongly agree. One's just a more stronger, higher agree. One's a, oh man, I'm totally on board with this, and the other's like, yeah, I can see that, and I agree. You're not really, you're kind of lukewarm. And neutral is like everywhere in between. That is ordinal scaling. Ordinal scaling is also income brackets. If labeled as working, middle, upper, or whatever, right? If it's labeled as numbers, then it's interval or ratio. So let's move on to interval or ratio. Interval measured as equal units number between them. What do I mean by equal units of measurement between them? Well, 1 and 2 are 1 apart, okay? 3 and 4 are also 1 apart. 5 and 6 are also, you guessed it, 1 apart. So if things have equal numbers between them, it makes them interval. Okay, that is a big point of interval and why it makes something interval. They must have equal units of measurement between each measure. In other words, 1, 2, 3, 4, 5, 6, 7, because each number has an equal amount of space between the other number. Temperature is another thing that can be measured at interval level, but only if you stick to one thing. Okay. So, and we'll move on to that with ratio, okay? So, ratio is everything that is in the interval level, except the ratio also features the 0 point and under. This is the highest level of measurement, and you can always go down while converting levels of measurement, but never up. Now, let's talk about certain things that does not have equal points of measurement between them, okay? So, temperature, when you're looking at scaling between Celsius and Fahrenheit, 1 does not represent 1 in as it does in some temperatures. It's not an even trade, okay? Think about it that way. So let's move on to the next PowerPoint. Central tendency, which is part of your homework assignment. And I know it's due tonight, but we'll move with it. So what's central tendency? It's the standard of our mean, the median, the mode. Right? That's it. Mean, median, and mode. Central tendency refers to the value or one in which most values tend to cluster, and variability is how numbers are dispersed. Think of a graph of points. Shape of distribution is how values vary in distribution. So the mode, what it is whatever thing occurs the most. It doesn't always have to be a number. Again, you can have a mode of brown eyes if you have more brown eyes in an audience. So in this set of scores, 58, 82, 82, 90, 98, the mode is 82. So useful for working with nominal level data, not much more beyond that. The mode's actually not that useful. We just learn it to kind of measure categorical stuff. There's better ways to measure categorical stuff. You cannot measure, well, you can, but it's not very useful. We'll use other things like standard deviation. The median is the thing in the middle, or the 50th percentile, okay? So the 50th percentile is just whatever, you arrange your numbers in order from smallest to greatest, okay, or highest to lowest, whichever way works. And if the number of cases is odd, then the median will always be in the middle case. If the number of cases is even, then you take the middle two numbers and you average them together, and you get the median doing that. So, if the middle two numbers are 52 and 52, then what you do is you take 52 plus 52 and divide them by 2, and guess what? That equals 52. So, cannot be calculated for variables at the nominal level. Why cannot it be calculated at variables at the nominal level? Well, that's because in order to get the median, you have to rank order things. And if you recall, the nominal level does not allow you to rank order anything. Percentiles. So remember how we were talking about the median? The median is in fact the 50th percentile? Well, If you want other numbers besides the 50th percentile, we can just call them percentiles, okay? So if a score is reported the 55th percentile, then that means that the case is higher than 55% of scores in that distribution. To find find a percentile, you have to arrange the scores in order, then multiply the case by desired percentile. For example, you can find the 46th percentile by in a distribution if you multiply it by 0.46. So as an example, 78 by 0.37. So let's say there's 78 cases and we want to find the 37th percentile, then you do that there and you can figure it out from there. The average. Now you're going to see a lot of formulas that look scary in this class, but I promise you it's not. Now, the mean is something you start to learn, I believe, in the 6th, 5th, or 7th grade or something like that, right? And that's the formula that they never show you to what the actual, what the mean is. And what that is sigma of x divided by n. Okay, sigma is simply means the sum of. Okay, so the sum of x divided by sample size is how that is. So let's say that you have a sample size of 5, and then the numbers are 2, 4, 6, 8, and 10. So you add up 2 plus 4 plus 6 plus 8 plus 10, and then divide it by 5. Again, you have 5 numbers, which is the divide by 5 part, and then you add up all the cases in the sample. So 2, 4, 6, 8, and 10. So 2 plus 4 is 6, 12 and plus 6, 8 is 20, and then 30. And then take 30 and divide it by 5, and then we have our mean. Inferential statistics are tools for drawing conclusions about the population based on observation from samples randomly selected from populations. There are many methods to random sample picking from a hat, using a program, so on and so forth. Let's overview types of random sampling, shall we? So first we have the simple random sample. You could do a simple random sample by taking every name in a population. We'll go back to the class of the population and throwing them all into a hat. And then we shake the hat up and we pull a name from it. That is a simple random sample because we had an equal chance of pulling every name from that hat, and each case is independent in the selection of each other case. What does that mean? What is the selection of each case is independent of the selection of each other case? What does that mean? That means every chance that you do, you put the name back in the hat. Okay? So if it would be dependent on selecting let's say that you pull a name from a hat and you draw it and you don't put it back, suddenly the next sample is now dependent on the fact that you drew a name. It is now at increased odds to draw everyone else's name because now let's say we had 20 names in a hat. Well, now that we have 19 names in a hat, then I'll go ahead and show you this on my own. Maybe see if my calculator will show. There's my calculator. So let's say that we have 20 names, okay? Now, if we draw one name out of this hat, it'll be a 1 in 20 chance or 5%. Now, let's say that we remove one name because we drew it, and now we had to draw a name now. And now it's a 1 in 19 chance to draw that, which is a little bit higher than 5%. Now, let's say that we draw 10 names out of it, and suddenly when the next one has a 1 in 10 chance, it is a 10% chance. So as you can see, as we remove names from that hat, the next name is subsequently higher odds to draw. So the bolded section represents what is known as the independence of selection. If we want a true simple random study or a true random sample, we must put the name back in the hat so that every other name has that equal and independent chance of selection. So the independence observations asserts that pairs of groups of cases do not share some unmeasured factor that makes scores more similar. Two students cheating on an exam is part of this violation, and test results will become too similar, and this wouldn't be a case had they not cheated. It interferes with the actual sample. Sampling error and sampling distribution. If you ever want to calculate your sampling error, it's sample statistic minus population parameter, and sample statistics only estimate populations and parameters. So, for instance, due to the luck of draw, the mean in your random sample of child abuse and neglect almost assuredly differs from that in the population. So, what do I mean here? Let's say I'm going to pull up a spreadsheet. Go to the blank book. So, let's say that let's close that. All right, let's say that, go back to the slide example. Random sample of child abuse. We'll just do age in the classroom, okay? Make it simple. Let's say that we have 10 students. Student 3, student 4, student 5, student 6, 7, 8, 9, 10. ID. And then we can name. We'll just do age because we're not too worried about age. So age, we'll say 20, 19, 21, 23, 22, 21, 24. This is me just inputting data. You'll see that data here in this case. So let's do a random sample of 3. So random sample of 3. So we're going to pull this, and we'll say that. So we're going to do a random between 1 and 10. And what we're going to do is we're going to take the top 3, the bottom 3 numbers. The bottom 3 numbers in this case are 3 ones, 4 ones. All right. So our random sample in the first sample is 20. It changed. Okay. It will do that. So let's go ahead and it'll be 18, 24, and 21. So 18, 24, and 21. Now we'll do another sample, the bottom 3 numbers again. 2 would be 24, 18, and 20. 24, 18, and 30, and 20. We'll do another random sample, the bottom 3 numbers once again. So 2, 2, and 3. So 22, 21, and 18. 22, 21, and 18. We'll do 5 samples. 23, 20, and we'll go 19. 23, 20, and 19. 23, 20, and 19. One more sample. Bottom 3 numbers is 2 would be 23 and a bunch of 4s. 23, 20, and 24. 23, 20, and 24. All right, so now we can get rid of this. We'll go ahead and delete that. Now we're going to do an average, equal average. Highlight that. Enter. 21.5 is the sample of our population. Now we're going to do average as our samples, okay? So equal average (21) for this one. As you can see, the average is 21.5, but we have a bunch of different averages over here. So now we'll take a look. So the mean, the error is sample minus population. So sample pop. So our population is 21.5. We'll go ahead and paste this, values only. And our sample, in this case, we'll just go ahead and copy this, paste these as values only. So again, sample minus population. So we'll go ahead and calculate our error term right here. Sample minus population, enter. And you can get negative numbers. Go ahead and copy this down. There we go. So which one has the highest error? Which one is the most accurate? Our first sample is the most accurate because it has a sample and an error term of negative 0.5, whereas the other ones have higher and negative have higher errors. And it's all about distance from 0. So this has less distance from 0 than this. So our best sample is sample 1. Now we can keep doing this and we'll graph it out and I'll show you how that works down the line. The central limits theorem, and you can click this and you can see how the central limits theorem works. And I think that's it. So you can watch that video. This concludes the recording of our lecture. If you have any questions, please don't be shy. Goodbye.